Hello viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about magnetic levitation as metro. So let's dive deep into it. Now, first, exactly why the heck we had we have to go to magnetic levitation in order to solve this problem? Well, reality is friction is a massive energy drain on a system. For example, if I give you 10 megawatt hour for your locomotive, how much of that energy was spent on actually moving you forward, pushing air out, and how much was spent on the friction? Friction is high. So that's why you do not need like 50,000 horsepower to make a plane, because it's not fighting friction. So fundamentally speaking, you can, if you have the same amount of energy, if you can remove the friction of wheels and all that, you can actually fly very fast. So fundamentally, what if you're floating? What if you're just floating? You're not touching it. Basically, you are an aeroplane that is constrained to the ground. That's it. So you can achieve speed that is almost like an aircraft and a throughput that is almost like a train, meaning you will not have to worry about wheels, bearing, slowing you down. For example, can a TGV run at very high speed? Like, can it touch 500 km per hour? Yes, it can. Will they give you service at that speed? Hell no. Why not? Bearings have exponential heating, meaning if you're running them, let's just say 1000 RPM, they're cool, they're fine, depending on the design and loading and all that. So if they're designed for 1000, they're cool, awesome, fine, no problem. If you push them to 1500, you would think, okay, it's a bit more. No, exponentially more. It will start to heat up exponentially more. So RPM has this inverse proportionality with heat generation with every component. So if you can help it, you do not want to go at very high speed. Of course, testing, validation, those things are awesome. But for service, you have to make sure that service intervals are not stupid. It's like, oh yeah, we gave this train in actual, line service, and every 3 months we have to change every bearing. Yeah, that's not acceptable. So that's the end dream we have. Speed of an aircraft, capacity of a train. Because even if you take a big giant puppy like Airbus A380, a train can be like, bruh, that's like nothing. That's just nothing. And on top of that, it can be powered by renewable energy. That's a very big deal for a nation. You do not want your nation to be dependent on some canals, and boom boom happens in that canal. Let's discuss Strait of Hormuz, and boom, your ticket prices go up. You do not want that. So if you have the ability to run them in solar and wind and nuclear, hydro, whatever have you, as long as you can run it on power and you have multiple sources of power, you get control over it, you get stability over it, and that's a good thing for a nation. Because be mindful, plane has a starting cost, as in when you are traveling for a plane system, starting your counter from airport, like you enter the airport, boom, start the counter, enter the railway station, start the counter, railway will be much faster for a distance, and that distance is directly proportional to the speed. For example, if the train is only traveling at 100 km per hour, that train makes sense for something that is like 50-60 km away. You can fly that. Katy Perry, I think, does fly that far, 50-60 km in a private jet, but does not make sense. It just takes too long. While a train makes more sense, because it's like, hey, but if you increase the speed 200 km per hour, 300, 400, now it starts to make much more sense. It's like, hey, I can travel that much. It's like, can't plane go faster? Plane is 800 km per hour. Yes, but you will lose so much time waiting before you start to fly, and landing, waiting for your luggage and all that. So all that translates into you experiencing much slower distance. And you can notice that people generally don't, in India and in Europe, people generally don't travel nearby with airport. You can, it's just unwise, go via train. So train has that ability. If you can increase the speed, the sweet spot expands, and you can have more and more people utilizing this puppy rather than burning foreign fuel. So history of this idea started from Robert H. Goddard. Basically, Elon Musk stole his idea. Yes, he is the one who created the idea of Hyperloop. Fact train, he used to call that. So he popularized the idea, and after that, Emily Blanchett actually make a physical prototype and has the patent and everything. Like, he was actually serious about this. Like, we actually made it, things were ready to go, and full-scale test of this idea of Hyperloop, Maglev, that happened in 1979. Basically, first time people created a human-rated structure that was carrying completely magnetically floating, wheel-less, so to say, and Japan went all into it because again, Japan had that issue where it's like, we do not have enough fuel, enough dollars to buy fuel. So what the hell to do? So they went all in, they studied the whole world and they realized every country has very fast train. Britain had awesome steam locomotives, secondary grade diesels there, but they were also improving on that. So they had like awesome horsepower. Electric systems in Germany and all that, they were awesome in horsepower. All of them had this one issue. Their locomotives were throttled backwards. Why? Because tracks were dual use, meaning freight was being traveled on the same tracks as train. And they were like, okay, we're gonna switch this, do that. Yeah, that was messy. And Japan was like, okay, we understood that. Trains are not the problem, it's the track. So they're like, okay, we're gonna make Shinkansen track. Track was the expensive part. They did the mathematical calculation, overbuilt the track, as in, even though their locomotives were only capable of 200k, they built day one track. Okay, how good the track has to be, as in like gradients, curvature, all of those, they flattened it out and they made sure there is zero crossing in that system. Zero. They knew even one accident will cost so much more money that is like, yeah, it's better to pay extra in upfront cost rather than, oh, we had a high-speed railway fail simply because we had 1 or 2 accidents. That's how sensitive it is. So they're like, okay, let's just make sure no crossing. There is only one crossing and that's only going to the yard, and there are police blockading it when they actually transfer the vehicle for maintenance. So fundamentally, they learned that track was the weak link and they built it. It worked. People are like, whoa, you're telling me people can use a train, trustworthy, reliable, far quicker than airports. And meanwhile, this is like early 80s. So people are like, what the hell? And Japan went all into it. They were like, okay, we're going to make Mach 1, Mach 2, Mach 3. And then like, yeah, sir, we know the upper limit of the tracks. We can't push beyond this. Like, and again, wheels have an upper limit. It's not like, okay, now make a even more straighter track. Yeah, you can't do much. Like they knew very early on that there is upper limit. You could push it. You can't give it as a service speed because it will cost too much wear and tear. So they got into, what if we went to Maglev? They went all in. The idea was 400 kmph plus as a service speed, not a prototype demonstration speed. No, as a service speed minimum, meaning if they can go higher, they will go higher. They will not go below this. So, and the whole point was the real world use case would be 2x compared to what other systems have. Like it will have a tangible benefit. Basically, the sweet spot will expand even further. And Japan is a tiny nation, like geographically speaking. So if they can increase the sweet spot, it almost becomes a point is like, there is no real reason to fly domestically. Like they could expand it to that much. Again, you can fly domestically to remote areas, but you don't have to, if this train is connected, which is traveling more than, in this design testing, they are touching 500. And be mindful, tracks are designed in such a way, day one, that they can sustain 600 or 650 without an issue. And there is no wear and tear on that. So that's the history of it. Now, while that being said, people are going super duper fast. There were parallel development. Basically, that is electrodynamic system. This is an electromagnetic system. Basically, you just have electromagnet that is actively pulling you up. So this was what we call low speed maglev. These are maglev. Yes, they are floating on magnetism, but they're not high speed. They're not even designed to cross 100 kmph. All of them are designed for that speed. Basically, they are for metro. Now, why would somebody develop a maglev for metro? Well, there are certain unique advantage. Again, is it important to you? That depends on your nation, your culture and all that, but it does have some advantage. One of the biggest advantage is that it is very low noise for people who are inside and people who are outside. For example, you must have seen this is as a meme that, you know, New York has that. How do you know you are poor in New York? You are living next to a subway and it's vibrating, it's noisy, it's brutal. I think movie 7 even had that idea. It's like only 6 minutes. Why? There is an extra, the whole building shakes and all that. So if you want to create a metro station in a densely populated area, you can't justify destruction of people's quality of life because, oh, I'm reducing this problem. It's like people are like, just let me use, you know, cars and all that. So that is a big advantage. Depending, again, somewhere you can just brute force it. Some places like we can deal with it. Other places like actually work their ass off to contain the environment. As in metro is moving, they're making sure everything is sound absorbing material. So you have a better source of what you call work with this, where it is not making sound itself. Now it's not 0 dB, but it's low enough where it's like nobody will complain. and better start-stop performance, because again, steel wheel which has low friction, that's the good part, but bad part, it has low friction, meaning starting and stopping is brutal. And because this is magnetically coupled, it does not care. You have leaf on the tracks, it does not care. If you are like, why the hell leaf is a problem, ask your UK friends. It's a brutal problem. This puppy is like, bro, I can tank snow, I can tank rain, I do not care. So there is genuine advantage in better start-stop performance, reliability, and it can handle much stronger gradient, meaning you're like, okay, what if you have to go like this? You can do that. It's almost like in the same flexibility as Mexico City trolley bus systems, where they're like, hey, we have dedicated, but like, can't you do metro and all that, tram or something like that? No. Because if you have a tram which is steel wheels on steel, the gradient slopes that you can tolerate is much loose. This puppy is like, whew. So that is an advantage. And tight curve also, because it's not like there is no fixed axle, it can take a tighter turn. As long as you can physically fold it, it's like, bro, I'm good. So there is some advantage. And to keep the cost down, because one of the biggest hurdle with electrodynamic systems is that how the heck you send electricity to it. Now, like, okay, it can have pantograph. Technically, it can, because again, TGVs have proven that it can push to that speed, pantograph at that speed. You could do that. They're like, yeah, if you really want to have zero wear and tear and give a service speed, it will not work. So they have to have wireless charging coils throughout the track. Now, again, if you try to do that on metro, that's bankruptcy. So they're like, okay, we're just going to put a third rail. So the train is floating and it has a stick that is going, the bottom stick is like, shh. It's just like, shh. You can, and this is from South Korea. It's like, shh. This is China. Shh. They always have a third rail. They are holding the rail. The track is floating. Let that be. The coach is actually floating, but they are touching this like, So, and most of the sound is coming from that, where they're physically touching it. So it does use, and why they use third rail? Because it's cheaper. Okay, it was designed from day one for a different market. It's like, okay, what has to happen? Like, people did try to, like, what if we have superconductor? It's like, no, you're not gonna put a goddamn MRI machine on a goddamn metro system. Yeah, that's how the Chinese and Japanese systems are like, okay, we have this superconductor. Awesome. How do you keep it cool? We dunk this puppy in liquid helium. It's like, cool, awesome. How do you cool the liquid helium? We dunk this puppy in liquid nitrogen. How do you cool the liquid nitrogen? We run this puppy with a cryo cooler on board 24/7. Yeah, no. Simple, third rail, go home. That's why it is electromagnetic, not electrodynamic. Now, electrodynamic does have the advantage. This puppy cannot float too much. Barely gives you 8 millimeter. Like, these are almost touching. While electrodynamic, and again, that does limit the speed. That's why it's not very high speed. At high speed, inertia will force it to the, and magnetism has upper limit, how much force it can handle. While electrodynamic, the higher the speed, the better it becomes. So if you're traveling 600 km/h, it's like, I got you. The cushion, the magnetic cushion you have becomes stronger. So like, whoa. And that's why they can float around 10 centimeter from the guide rails. So again, like, yo, and what if they are taking a turn and it's like, yo, G-forces are like pushing the chassis. The magnetism is like, bro, inversely proportional. I'm stronger now. So that makes sense for high speed. This makes sense for low speed. Ironically, this is the design used in Shanghai system, which was stupid. But again, that does travel faster. This does not travel faster. There are, I think, 4 or 5 metros that are like this. So we talk about another funny one, that is Linimo. This is in Japan. This was created in Archie 2005. And the whole point was they are supposed to work in an Expo 2005. And it's a driverless 3-coach car. The coaches, there are 3 coaches, driverless, 43 meter long, and it's not a commuter link. Let that be very clear. This was designed as an attraction. It is an attraction. It's not a bulk carrier. It's not. None of the systems are bulk carrier here. And it has 9-kilometer length and 9 stations. And be mindful, it's not directly Japanese railway. It's nor completely private. So it's a mashup, I think, public-private partnership sort of deal. Now, tracks are very expensive. Now, like, why? Isn't it supposed to be cheaper? You do not have coil, you do not have weight and all that. Yeah, it is not that expensive, but all the price goes away. All the benefits goes away the moment you have to switch the track. Switching the track is not an option in this. Like, these switches are so goddamn expensive, it actually would make more sense to just buy a land and have a loop. But again, you can't. What if any train breaks down in the between? You can't do anything. Switching, like, it is difficult. Like, they have to switch the whole guideway. All the savings of this goes away. The moment you have to switch the track, all the thing, everything, like first this bends, then that bends, then the central part pivots, it pivots, all the savings, everything goes away. This is the primary reason why monorail does not work. It's like the moment you have to switch the tracks, you're like, yeah, all the benefit goes out of the window, all of it. Oh yeah, this can handle all the snow, this cannot. If heavy snow happens or this happens, you have to overbuild this puppy so much that it's like, okay, what if it snows? Like the hydraulics have to like, what if it's like rains like crazy? Everything, all the savings you had on the system, on the coaches, on the tracks, just this. Look, the videos are available, you should check it, but you'll find it's like, this will make sense why nobody does this. If we have figured it out, technology is a thing, 2005 kind of thing, why don't we use it? It's just that it's a driverless, you don't even have a labor shortage. But again and again, it's a very good for tourism, because you can just stand there and see the whole tracks and all that. So is there, all the savings goes away in the track. So what's the reality? Reality is, when you're talking about high-speed train, it's not the wheels that are your enemy, it's the aerodynamic system. That's why Robert Goddard imagined that, like, we're gonna have either low pressure system or a vacuum system. At high speed, that matters far more. Again, at slow speed, frictions does matter, but at higher speed, anything above 200 kmph, you would be shocked how much drag is applying effect on you. And be mindful, higher your speed, like 200, 300 km/h, which is normal for a high speed rail, at that point in time, friction is a consumable. It's not big deal. It's like, yo, this is my budget. This much is on a friction. You save this much, it does not matter. So fundamentally, Maglev does not give you enough savings, and not to mention it fight backs on you, because if you're building a Maglev, you're not gonna run it at the same speed as normal high speed. You have to run it at faster to justify it. And there lies the problem. Speed has exponential drag coefficient, as in the faster you go, the exponentially more energy you have to deal through, meaning Maglev system that is going YOLO at like 400 kmph, it's not just a bit more, like 25% more energy draw compared to 300 km, it's exponentially more. So that creates an issue. So, and contactless power transfer, that is expensive. Runway for EDS electrodynamic systems, again, they fundamentally cannot start below 100 kmph. Let's say they can propel you. They can propel you from zero, that's not an issue. They just can't levitate you at 0 kmph, like electromagnetics. Electromagnetics is like, I got you. It's a closed loop, but it's not stable enough for very, very high speed. And you can do that, but you may not want to do that. It's like, what if something goes bad in the control loop? What if you want actively stable system, not passively stable system, where it's like, okay, I'm controlling everything. It's like, no, it is stable. You touch it, it's still stable. You don't touch it, it's still stable. So EDS gives you that. That's why like 10 centimeter wiggle room, that does matter a lot at high speed, because a wind gust should not cause a system failure. So that is there, that's a good part. But again, it does require wheels that can carry the whole goddamn train, MRIs on wheels, and it should fold up safely at 100 above 100 kmph. Basically, they detect there is no load on it, fold up. Emergency brake, deploy before train becomes slower than 100 kmph. So, and here's the deal, remove all of that, okay, throw all of that away. Tracks are the expensive part, and that's why people who actually work in locomotion, people who work in basically urban planning and railway system and all that, they knew day one Hyperloop was never going to work, simply because track is the expensive part. It's not the technology that is on the track, it's the track itself, because we humans have a limit. For example, can you make a train that can turn and twist almost like a metro, almost like a bus, and do that at 700 kmph? Of course you can. It's easy peasy. Fighter jet engineers would be like, bro, that's a Wednesday for us. That's easy. Then why don't we do that? Yeah, you're gonna be dead inside. So fundamentally, to have normal people normally ride a train, the train track curvature becomes limited, the turn become limited, gradient become, even if you're like, okay, everything is straight, but it does have like, I have to follow peaks and valleys. No. You have to make sure it's a straight line, because if you're traveling at 600 kmph and go whoosh, whoosh, yeah, 5 to 6 people will go completely. So tracks is the whole point because of the hygiene, meaning the layout constraint that you have. When Shinkansen was built, that was designed for 300 kind of speed. But when they are building this 600 kmph design system, they're like, yeah, we can't actually build that. It's like, it has to go through mountain, meaning you should be able to point a laser from one end to other end and it will go. And if there is a curvature, that means a station is coming up and you're slowing down anyway. Otherwise, you have to make it absolutely straight. So When you compound all of those variables, you will understand why this thing was. I used to watch this in Discovery Channel when I was a child. I'm 33 years old, and it still not has happened. This has like so much money burning in Japan. This literally made Japan more expensive to live. Like it burnt Japan alive, and Japan is like, we're gonna burn this. Like that's how government used to justify this. Like we're gonna develop this technology, we're gonna sell it to other country. Not even China bought it. Like yo, this is too stupid. They built it. They have the whole ecosystem, but they're like, because again, to make it tracks cost effective, you have to drop at 300 kmph. At that point, just use normal high speed. If you have to justify this, you have to go to like 400 or 500. At that point, tracks become exponentially expensive. And this really has very high energy draw simply because it's going through a tunnel. Basically, it's an air compressor. So fundamentally, speed does not matter if it brings bankruptcy. We are building this technology, it's burning so much money away that we are destroying the youth and we are removing their will to live and we are reducing their ability to bear children. Yeah, it does not matter. Like corpses is gonna ride on this. So that's the reality of it. And again, I saw a lot of comments in the basically why they are doing trolley bus, not just electric buses. Like trolley bus is dirt cheap. A battery bus is ludicrously expensive and ludicrously short-lived. We have trolley bus system from Soviet Union still working. You don't see battery bus lasting that long, and it won't last that long. Fundamentally, it won't last that long. It's a consumable item. So even if you have battery, you want it to be like just a emergency. It's like an emergency battery. Hey, when I have to go to yard and all that, then that's how you use it, not on full load system. In that scenario, battery will last 10 years. If you use it like full heavy load, yeah, good luck. Oh, not to mention, the bigger the battery, the quicker the degradation of the whole structure, chassis and all that, and not to mention the infrastructure you built. So that's why right tool for the right job. Can you make a Maglev metro system? Yes, people did do it. Can you make a hyperspeed system? Of course you can build it. It's just that all of them will bring bankruptcy. So this was my presentation on basically Maglev for Metro. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, urge you to press dislike. Press it twice to show me assessment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, press the hype button.